Good morning, everybody. Welcome back to Galois Theory. How are you all doing today?
Sick but better.
How are you doing?
Glad to hear it. I'll take it. Sick but better. Plan for today is we're going to try and I don't think we'll quite finish chapter 2 today, getting through irreducibility criteria, but I think we can get pretty close so that next time we can start chapter 3 and actually start getting into some Galois theory proper with field extensions and such.
Very, very cool.
Which is very much related to what we're doing today. Plan for today, today's going to be less proof-driven and more example-driven. Shamus is here. Homework. Yeah, homework 2s are back. Take a look at them. My solutions are posted on Canvas. I'll try to get 3 graded by next Tuesday. It's probably the most likely time you'll get that practice. Yeah, homework 4 basically what we're doing is over basically what we're doing today and what we've done in the last couple classes, so have fun with that. Questions, comments, concerns? Eleanor.
No, I'll just get some notes after class.
My notes are on Canvas too.
Oh, cool. Okay.
So, alright Eleanor, why was 6 break 7?
7, 8, 9.
But why did 7 eat 9?
That's an excellent question.
Lincoln?
Because he knew the value of 3 square meals.
He knows, because 7 knows the importance of eating 3 squared meals a day. Alright, and with that, let's get to it. So last time we proved a couple of major theorems regarding irreducibility. We proved that all irreducible polynomials over the reals have to be linear or quadratic, though not all quadratic polynomials are irreducible over R, as we've seen. We also proved that irreducibility over Z, for an integer polynomial at least, is equivalent to being irreducible over Q, which was our second major result last class. That was Gauss's sum. So today, I'm going to look at a fun little result here called Eisenstein's criterion and see if we can, we have one short-ish proof, and then we're going to, basically the rest of the class is going to be playing around with a bunch of examples. Sound good? Of course it does. So, Eisenstein's criterion for irreducibility. Suppose you have some integer polynomial, your coefficients are relatively prime, and you can find some prime p where p divides all of your coefficients except for the first one, and p squared does not divide your last coefficient. And in that case, f has to be irreducible over the ratios. So if you can find some prime that divides everything but your first coefficient and doesn't divide your last term twice, your constant coefficient twice, then it has to be an irreducible polynomial. So what would be an example? Something like, I don't know, x cubed minus 10x squared plus 30x minus 40. I claim this is irreducible by this theorem. So what would be an example of a prime that doesn't divide the first coefficient, just 1, divides everything, divides 10, 30, and negative 40, negative 10, 30, and negative 40, but doesn't divide 40 twice? James?
5.
Yeah, 5 divides 10. It divides 30, divides 40. Doesn't divide 1, not in the integers at least. And if you take 5 squared, that's 25. That doesn't divide 40. So p equals 5. Eisenstein's criterion, boom, this thing's irreducible. How about that, Emily Rose? Yeah. So we could just say irreducible by Eisenstein. Equals 5. Questions, comments, or concerns about that? So where do all these conditions come from? Well, it really comes from, if we try and prove Eisenstein's criterion, which we'll do in a second here, it kind of comes from what are all the different pieces that you need along the way in order to guarantee that something happens. So let's try and prove Eisenstein here. And as part of our proof, what we're going to see is that, how do I put this? As part of our proof, we're going to end up seeing how each condition kind of necessarily pops up as a step along the way to giving us a result. So here we go. Here's our proof. We're going to let f of x be defined as in the criterion. So we're going to assume we have some polynomial f of x that satisfies all of this for some p. And we're going to do a proof by contradiction, which basically means we're going to assume that f of x is reducible and show that something goes wrong, that one of these conditions has to break if we assume that f of x is reducible. So let's suppose f of x is g of x times h of x. For some, we'll call it g of x equals b sub r x to the n plus b1x plus b naught. H of x, we're going to call c sub s x to the s. Excuse me, this should be b sub r x to the r. Plus c sub 1x plus c naught. So in other words, we're starting with an f of x over there, and we're assuming that it can be broken up into a product of two non-constant polynomials, g and h. We need to somehow go through our laundry list of conditions and show they can't all hold.
G and H are in the rational polynomials, right? Okay.
Yeah. Well, they have to be. Or can we restrict ourselves to just looking at integer polynomials?
Oh, well.
Given what we know from last time, that for an integer polynomial, irreducibility over q is the same as irreducibility over z, I think we can assume they're integer polynomials. And show that if we have a contradiction where they're both integer polynomials, then we necessarily have a contradiction where they're rational polynomials as well. N'est-ce pas?
Sure.
Maybe. And in fact, we're actually going to want these to be integer polynomials. Because we're going to start talking about p dividing coefficients of these and such, which doesn't really make sense to talk about over the rationals. There's someone else had a... Matthew.
How do we know that p, like just for this example here, like if we're dealing with ginormous numbers or something, like how do we know that p equals 5 is the p we want to work with? And like, because it's irreducible Eisenstein when p equals 5, but like could it also, for a different prime, could it work out in a different way?
Sure. For instance, it almost works with p equals 2. If I were to replace... Actually, there's nothing I
No,
can replace
there's
this with
nothing.
that would work there. But if we tried p equals 2, it satisfied bip and bop, just not boop. So actually, yeah, no, we could just do... let's just do 30. P equals 2 or p equals 5 would work in that case. So how do you know which one to work with?
Yeah.
You don't necessarily super easily. I mean, that's why you have computer algorithms that work all day on trying to do these sorts of things. And if you want to learn more about this topic, take cryptography this fall at 425 with me. Haha.
Does it matter which one you choose?
It doesn't matter which one you choose, but how do you determine what p will give you all these conditions is a tougher question. For all the examples we're going to be looking at in this class, we're mainly going to be looking at ones with relatively small coefficients. But there are cases like in cryptography, for instance, where you will be looking at polynomials where the coefficients can be like hundreds of digits long. And in that case, choosing your p is a completely different question, and one that's not so easy. And if they're all even, try p equals 2 is a good thing to try. But
Does P tell you anything about how it would reduce in the real polynomials?
reduce in the real
Like,
polynomials?
if this doesn't reduce in the integers or the rationals, but what about reducing in the reals? Can it do that?
Sure. I mean, we know this is reducible over the reals because everything that's non-linear and not quadratic does.
Right, but does P tell us anything about how it would reduce, or is it just
Not really.
okay?
I mean, you could say that p is not a root because if it was, then the fact that it divided all of these would mean it also has to divide a sub n. So like you couldn't like factor out an x minus p, for instance, but it doesn't really tell you what does it factor into super easily.
I'm just trying to figure out if P is like a property of
P for prime, not property, just like q is for rational and not
Okay.
quotient.
Okay. Okay. Just because I remember things on a first letter basis does not mean
Just because I tried my shortcuts don't always work. Alright, let's come back to the proof here. So we're assuming f of x is reducible. First thing I'm going to use is n. And p divides a naught. And say, what's the relationship between a naught and the terms in these two polynomials? Elmar?
It's B naught times C naught.
Emily Rose?
I was gonna say the same thing.
Then since f of x equals g of x times h of x, a naught has to be equal to b naught times c naught, because the constant term of the product of two polynomials is just the product of their constant terms. So since p divides a naught, what does that tell us? If p divides b naught times c naught, and p is prime, James?
P squared divides a naught.
B squared divides a naught. Uh-oh.
Oh.
I don't think we're going to get a contradiction that quickly.
P divides either B naught or C naught.
Right. My brain.
Yeah. We know P has to divide P naught or C naught.
Sorry.
Yeah. P has to divide either B naught or C naught because it divides the product of the two. And what it means for an integer to be prime is if it divides the product of two things, then it has to divide one of the two individual things. So P divides AB implies P divides A or P divides B or prime.
But P divides A plus B.
Oh, if P divides A and B, then it'll divide A plus B. Question.
Or else you know absolutely nothing about
Can
it.
P divide both B naught and C naught?
No.
Andrew?
No, because P squared does not divide A naught.
If P divided both B naught and C naught, we would get that P squared has to divide the product of the two A naught, which we know is not the case. So P can only divide one of these two things.
So I'm gonna be a programmer and write P divides B naught XOR P divides C naught.
Okay.
XOR is not real.
I'm just gonna say since P squared does not divide A naught, we know you can't divide both.
But XOR is equal.
And without loss of generality, we'll assume B naught's the one it divides. So voila, again voila, short for without loss of generality. Just call B naught the one that P divides. P divides B naught, but P does not divide C naught. Cool. We use this condition. So far far so good? Groovy. So now, I'm going to have a claim here. My claim is that P must divide each B sub I. That if B naught is the constant term out of the two of these that P ends up dividing, I claim P has to also divide B1, B2, B3, up through B sub R. Why is that?
Is it because when you multiply g of x and h of x, all of the h of x, or all of the c sub i's are multiplied by b sub 0?
Essentially, yeah. Essentially, yeah. This is actually not like a one-line proof or anything. We're actually going to prove this by induction. So here's our proof of the claim. We're going to suppose that P divides B naught, B1 up through B sub K minus 1 for some 1 less than or equal to K, strictly less than R. And our goal, actually no, K can be equal to R. And our goal is going to be to prove that P has to then divide B sub K as well. Well, so here's a question. What's A sub K to be equal to? If we were to multiply these two polynomials together, what would the coefficient on x to the k in our product end up looking like?
B sub k x to the k plus b sub k minus 1 c,
Not b sub k x c sub k.
b sub k c naught x sub to the k. I could write it down. I'm having a very hard time thinking it out.
Now there's no x's in here. This is just a product of coefficients.
Oh, right. So b sub k.
I know what you're trying to say.
Yes.
How about I just write it down?
Please.
Basically, b naught c sub k, and then you have products of BC's where the sum of the coefficients adds up to k.
Yes.
Plus b sub 1 c sub k minus 1 plus dot 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 plus b sub k minus 1 c sub 1 plus b sub k c naught. So if you were to multiply out these two polynomials, the x to the k term coefficient you would get would just be this sum. And that's just I don't know, binomial theorem expansion FOIL on steroids, whatever you want to call it. Not really binomial. So, what do we know? P has to divide a lot of things here. We're going to assume we know P has to divide that, and that, and that, and that. Not this. So what can we conclude from this? What else does P necessarily have to divide if it divides that, and not that? Elmore?
B sub k.
It has to divide B sub K.
How do we know it provides A sub K?
Good question. Whatcha?
Okay, so this was only.
We know that we're assuming that g of x, I guess maybe I should mention up here, we're assuming these are going to be non-constant. So that we're actually assuming reducibility.
Okay.
And in that case, both of these, R and S, have to be strictly less than n in order for them to multiply together to give us a degree n polynomial. Would you agree with that?
Yep.
And in that case, we know that k, whatever k we choose, is going to have to be strictly less than n, and P divides all the a coefficients except for a sub n, so it'll have to necessarily divide whatever a sub k we happen to be looking at. answer your question?
Yeah.
So yeah, that's what it comes down to. So then since P divides A sub k, B naught, B1, all the way up through B sub k minus 1, we know P must also divide the last term in this sum, because we could just subtract all this other stuff over onto the left-hand side of this equality and say, since P divides A sub k minus B naught C sub k minus B1 C sub k minus 1 minus dot 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 minus B sub k minus 1 C sub 1, it's going to have to divide what all that's equal to, which is B sub k C sub I. And since P does not divide C naught, well, P is prime. If P divides the product of two things, it has to divide one of the two things. Thus, P divides B sub k. Questions or comments about that? And then that basically proves the claim, because then we can just say by induction, we've shown directly P divides B naught. We've shown if P divides B naught, then P has to divide B1, and if P divides B naught and B1, then it has to divide B sub 2, etc., etc. So by induction then, P divides B sub I for all I. 1 less than or equal to I, less than or equal to R.
Is it less than or equal to R, given we're assuming that P does not divide A sub n?
Say that again?
R is less than
Okay.
Yeah, the R has to be strictly less than n, coming from the fact that we're assuming these are non-constant, so S can't be 0, so since R plus S has to give us n, R and S both have to be strictly less than n, since either one is 0. Everybody okay with the coin? Lincoln, you look like you're stewing over something.
Yeah, sorry, I'm just.
While you're stewing, I'm going to get a new piece of chalk, because all these are getting too small.
Well, there's a problem with it divide, because if it divides R, then it must divide n as well.
Why do they have to be non-constants? Is not all constants are.
Because
units?
constants are units.
No, but not all constants are units.
We're doing Cusin.
Oh, okay.
Have we satisfied Lincoln's problem?
Yeah, you know.
I didn't actually care, but I'm glad to hear it. Alright, so we have our claim. I'm going to erase all of this. So, P divides all of the coefficients in G of x. Watch my
Whisper.
So since P divides B sub I for all I, what else does P have to divide?
Sub R, which is a problem, because B sub R times B sub S is A sub n, which P should not divide.
Uh-oh, SpaghettiOs. Yes, P divides B sub I for all I. P divides B sub R. Hence, P divides. That out of I'm the only one who draws smiley faces on my board. I drew a lot of smiley faces in my 105s today. We had fun. Hence, P divides B sub R times C sub S, which is equal to A sub n, contradicting this one. Thus, f of x must be irreducible. What?
Than
Oh.
fence. Yeah.
What?
Buildings. Yeah, it's been doing that all morning. It's been doing that like all since I've been here
Huh?
for the last like 6 years.
Oh, the
I
super
like grounding.
Get over it. So this gives us a proof of Eisenstein, basically saying that hey, if P divides A naught, then and all these other A sub I, then you can show that if f of x were reducible, P would have to eventually divide all the coefficients in one of the polynomials. And if it divides all the coefficients, it has to divide the leading coefficient in one of these polynomials, which means P has to divide the leading coefficient of f of x. And if P divides the leading coefficient of f of x, then condition A ain't happening. So, Eisenstein's criterion. Clap for that. All right, that's our one proof. That's our one big proof for today. Let's do some. How about we do some examples next?
I like that.
All right, let's show some polynomials are irreducible over Q.
We should clap every time you finish a proof, actually.
I mean, if you want to.
So we showed that it.
Hi, Lydia. By the way, I don't think I said hi earlier.
Hi, Lydia.
Yeah, we just ignored her.
Yeah, sorry. What
So
is it?
we showed that if Eisenstein's criterion holds for functions in Z, well then they'll also not be reducible over Q for what we showed the other day. But what if it's in Q and not in Z? How would it even?
Oh no. Let's do an example and see if we can determine if we can figure that out. How about we look at f of x equals x to the fourth minus 5/3 x cubed plus 20x squared minus 10x plus 10/3. And our goal is going to be, I claim this is irreducible over Q. Oh, you just want to multiply everything by 3? I mean, you could say then that 3f of x is going to be what? 3x to the fourth
Okay.
minus 5x cubed plus 20 plus 60x squared minus 30x plus 10.
Figure P equals 5.
I was going to ask Matthew because he wanted to know, so I was going to give him a test. Matthew, can you see any primes P that would not divide the leading coefficient, but that would divide all of our other coefficients? 19 does not divide -5. Do not listen to Lincoln. He's a bad influence.
I was curious,
3.
could you also do -5 here too?
Whoa.
Ooh,
Oh.
Min likes that
What
idea.
yeah, Min, what do you think about that?
Yeah. You could say that's irreducible. By Eisenstein, P equals -5
Just stick with the girls.
over the integers.
So don't grab Min.
No.
Hence is irreducible over Q by Gauss's lemma.
Whoa.
That's like that thing in electromagnetic physics or something.
Yeah, that's like wait,
That's the big theorem from last time that said for an integer polynomial, irreducibility over Z is equivalent to irreducibility over Q.
sounds like.
I
Aw.
thought it meant that the electric field.
No. And so-
charges the net surface.
To answer your question, Matthew, although it might feel a little silly to do so, sure, P equals -5 totally works too.
Yeah. So, but you could also do the same thing for 5. But like, should you check both just to make sure? Like,
No, because divisibility by 5 in the integers is equivalent to being divisible by -5.
right. But if there's multiple like primes, is what I'm saying. Is it like should we try to check all the possible options before we say this is like purely irreducible here?
No, to prove it's irreducible, you only need a single P.
Okay.
And to apply Eisenstein, if you can find multiple P's, then cool, good for you. Like if we were to multiply, like if we had the same polynomial, but all of these terms were multiplied by 7 or something, you could have picked P equals 7 as well. But it only takes a single P to actually show irreducible.
So there's no like case in which you only get a P that like checks out, another P that doesn't check out.
Well, you could, but
You could.
You could, like, there's many, many values of P, in fact, infinitely many, I dare say, that wouldn't satisfy all three of these conditions. But the fact that there is at least one p that does is enough to say this polynomial is irreducible.
Okay.
When I heard from you today. Isabel, if 3f of x is irreducible over q, what does that tell us about f of x? Can f of x be reducible over q? If 3 times f of x is irreducible? So let's say 3f of x is going to be equal to some g of x times some h of x. What can we then say about f of x? And you can just write it as g of x over 3 times h of x in that case. And since we're talking about irreducibility over the rationals, that's totally a valid thing to do. So that would lead us to a contradiction pretty quick. If 3f of x was reducible, then f of x would have to be reducible as well. What point am I trying to make here? 3f of x is irreducible, therefore f of x would have... Hey man, I don't know what point I'm trying to make. I think the point I was trying to make is that if f of x was reducible, then 3f of x would have to be reducible. I'm sorry. Because if f of x is equal to some g of x, h of x, then 3f of x would necessarily be equal to, for instance, just take like 3g of x times h of x. So the fact that 3f of x can't be written in this way tells us f of x must also be irreducible. That's just an example.
Fur all over my notes now.
Oh, yes.
It's okay. Questions or comments about this? So Emily Rose, to answer your question earlier about like how does this work for,
You just pretend it's in Z and then you put it back into Q.
you just multiply, and take a rational polynomial, multiply by whatever integer makes it an integer polynomial. Then you can check irreducibility with Eisenstein over the integers, and then that'll tell you something about irreducibility with Q.
Whoa.
Wow. Holy moly. Let's do another one.
Crazy. Flash bumpers.
Let's do 10x to the 4th minus 30x cubed plus 60x squared minus 5x plus 30.
I don't think this one works.
I don't think it does either.
Oh, hold on.
Well, I mean, I don't know if it's irreducible or not, but I don't think Eisenstein works.
It doesn't. Oh, shoot. Only 3 divides that. 3 to,
Not to mention, if 5 divided all of them, then we'd have another problem.
Okay, can you divide it by x in some way to make it like
What if we
if you
subtract
have
it?
the
What if we just
Whoa! You just wrote them in reverse order.
I'm sorry, someone was asking a question and I ignored them to make it dramatic.
You wrote them in reverse order.
I was wondering if there's something turned one is
I prefer if we
Perhaps so.
multiply it by something.
No, I think we should just subtract 3 from both sides.
That does not help us.
G of x minus 3.
And then add 5x to both sides.
Let's try this. Let's suppose g of x is equal to h of x k of x for some k of x degree, we'll call it, why am I doing k first? H of x degree, and we'll call it a in the integer polynomials, and some k of x of degree b. You're right that we can't directly apply Eisenstein to g of x. Why? Because g of x is, well, there's no prime that satisfies all the conditions. Matthew, would you agree that no prime p can satisfy all of these?
Definitely not, but like, could you still use it to like prove its irreducibility? Like,
Oh, we're going to.
Yeah.
We just can't do Eisenstein on this as it currently sits.
Oh. But why couldn't you do it as it currently sits right now? Like, couldn't you just throw in 3 and just be like, it doesn't check out?
No, but, well, here's another thing. If all of this happens, f has to be irreducible over q. That doesn't mean if f is irreducible over q, then there has to exist some p that satisfies all these conditions. For instance, x squared plus 1. That's irreducible over q. But there's no p that satisfies all of these because, well, no prime number divides 1. So if all this happens, then f is irreducible. But if f is irreducible, we're not guaranteed to have a p that works. And in fact, this is going to be one of these cases where no p works, and yet f of x will show is still irreducible. Holy cannoli. So, how do we do this? We're going to get tricky. Instead of taking g of x, what's a way to make this? What's a way to take g of x and make it into a polynomial where all the coefficients, the order of the coefficients is reversed? Jonah?
Maybe let y equals 1 over x and then multiply.
We're going to do g of 1 over x.
Whoa.
Oh.
Wow.
Oh yes.
Oh. But this is not in the.
But that's not a polynomial, Dr. Gerstle.
Yeah. Wait.
We're also going to multiply by x to the 4th, so it ends up actually being a polynomial.
Yeah, but doesn't it just not have to be a polynomial? Wait, it kind of does. Well, I mean, does it have to be specifically a polynomial, or does it have to act like a polynomial?
I'm sorry, what was your question?
Does it have to specifically be a polynomial to satisfy Eisenstein's criterion, or can it act like one? Like, is it can
Act like one?
like can it be isomorphic to like the polynomials and still satisfy the condition?
Oh, I mean, if you have a ring that's isomorphic to the, like, integers or the rationals, for instance, sure, you could come up with an equivalent. You could come up with an equivalent version of Eisenstein that'll work over that ring as well.
Yeah.
Polynomials, sure. But it has to satisfy all the same properties.
Yeah.
Integers and rationals, etc. So, x to the 4th times g of 1 over x will give us 10 minus 30x plus 60x squared minus. I should probably not just go directly to this. So what we're going to get is we're going to get x to the 4th, and basically we're replacing all of our x's here with 1 over x's. So we'll get 10 over x to the 4th minus 30 over x squared plus 60 over x squared. That was supposed to be cubed. Minus 5 over x plus 3. And then you multiply that out, and you get 10 minus 30x plus, hey, 60x squared stays the same. Minus 5x cubed plus 3x.
Oh, look.
Hey, wait a minute.
We've seen that.
We've seen that before, and we know.
No, we haven't. We've seen 3x to the 4th minus 5x cubed plus 60x squared, dot, dot, dot. We haven't seen 10 minus 30x plus, oh, wait, they're the same.
Except this one is restricted to the domain without zero.
Which is irreducible.
Oh, that's true.
What?
We can't let x equal 0 because we've divided by it.
It's true, we can't like plug in x equals 0 into this and expect to get something. But we're not actually worried about plugging in numbers for x here when it comes to factoring.
We just want factors. Or rather, none of them.
Yeah, which is irreducible over z by Eisenstein, p equals 5 again.
From our sample set, I'm getting that P always equals 2.
Five is a really great number.
Okay, well the example I came up with off the top of my head just happened to be p equals 5. These two I explicitly constructed to be like, hey, it's the same thing, just kind of reversed.
I think it's
To
like
make a
just-
point.
I think
Plus or
all-
minus
All
5.
all
Sorry.
primes are equal to 5.
All primes.
All primes are
See, I
equal
would-
to 5.
Alright.
That will be all.
Jonah, could you prove
Alright, Jonah. You're a funny guy, aren't you?
What have you done?
Factor this for me
Um,
into two polynomials.
we know it's irreducible.
Nevertheless, the fact that g of x is reducible means that should have a factorization as well. And that'll be a contradiction. And that'll be our contradiction, which says that our original g of x had to have been irreducible.
So if h of 1 over x times x to the power of degree a, and k of 1 over x times x to the power of degree, or sorry, x to the power of b, I guess.
Yep, you got it. Yeah, so first of all, the fact that g of x equals h of x, k of x means h of 1 over x times k of 1 over x should be equal to g of 1 over x.
That's true.
Problem is, these things are probably not polynomials. So we have to kind of split, to make them polynomials, we have to split this up using the same sort of trick that we did here by just multiplying each one by the degree of the original polynomial to get them to be polynomials. So we can do that by just taking x to the a, h of 1 over x, times x to the b, k of 1 over x. And that be some element in here. That will be something here. And so we can conclude that if g of x was reducible, well then one of these would have to be, if g of, let me start that sentence over. We can conclude that since we have two different polynomials multiplying to give us g of x, if g of x was irreducible to start, that would mean one of these has to be a constant, which would mean one of these would be a non-constant, and we would get a contradiction.
Wait, why did you say that that's not?
At least, because if they were both constant, then that would imply what? That would imply that h and k up here had to have been constant. And the only way that can happen in all possible cases is if g of x is irreducible. Reducible.
Reducible.
That, the other one. Let's write some of this down instead of just trying to say this out loud.
Yeah.
So, if g of x was reducible, we could do this in a way where g of x, or h of x and k of x are not constant.
Because that's what it means for it to be reducible, right?
Correct. And x to the a, h of 1 over x, and x to the b, k of 1 over x would be non-constant. That would break that x to the 4th times g of 1 over x is necessarily irreducible.
It is vital that both of these remain non-constant.
Yeah.
The thing that is
Contradicting that x to the 4th times g of 1 over x is irreducible. So what can we conclude? We can conclude g of x has to have been irreducible. So it can't be reducible. Let me at least finish writing it.
I got excited.
Clap.
Two very different kinds
It's
of
like a
clapping
pulley
between
really
the two of you.
So, what does this tell us? Well, this tells us that if your coefficients don't satisfy Eisenstein, But if they do happen to satisfy Eisenstein written in the opposite order, then you could do this sort of trick and still be able to use Eisenstein to show your original polynomials irreducible, just with a few extra steps along the way.
Or even more general, with some sort of, because you did a transformation from one Eisenstein-able thing to a not. So there's probably some rule of what mapping keeps Eisenstein's criteria.
Or what mapping preserves Eisenstein, let's say?
Yeah.
I don't know, what do you think, Isaac?
Well, over there we plugged in a value. It's a single thing over x, but I have to think about it more.
While Isaac's thinking about it, let's do another example. And this one's more going to take the form of a theorem. But this is going to give us a whole class of examples that we can Eisenstein up.
Oh, yes.
If p greater than 2 is prime, so then f of x equals 1 plus x squared plus x to the p minus 1 is irreducible. Does anybody know what these polynomials are called? Polynomials that are of this form?
Irreducible.
Famous smack hit. Lincoln?
A Taylor expansion for e to the x up to x to the p minus 1.
I thought
That's not what I'm going for.
Well, they're quotient irreducibles.
Quotient? What was it? Now you're just being silly.
Like geometric.
I like that answer the best out of all the answers I heard so far, but that's not quite what I was going for either. Something that's specific to the case where p is prime. They're called cyclotomic polynomials. I was gonna say, Andrew, I wasn't sure if you had maybe heard of
That
this.
sounds like a
Cyclo what?
cyclotonic.
Cyclo what?
Encyclopedia.
Oh, is that
Oh, that is an M.
Cyclotomic.
I thought we were talking about like
Cyclotomic as in cycle, as in cyclic, as in
Whoa.
cyclic group theory might come into play at some point.
why is it atomic and not atomic?
Because, I don't know, a guy named Tom came up with it. I made
A
that up.
man named Cycloton.
The name's Tom, Cyclo-Tom. I'm a man named Tom who rides a bicycle. What can you say?
I also do math.
We'll get into this name later on, but it's going to have some interesting interpretations. I don't know why the atomic specifically. Alright, so so let's prove this. And this is specific to the case where where p is prime. If p is not prime, then it doesn't necessarily hold. Turns out we can prove this. We can use an Eisenstein to show it. Alright. Question. What do you get if you multiply this polynomial by x minus 1?
You get another polynomial.
Very good, Parker. What polynomial?
X to the 7, or sorry, x to the
P minus 1.
Yep.
Yes, there are no parentheses around P minus 1.
Correct.
Wait.
What is trust?
Well, it's because it's like the whole polynomial is shifted by x,
It's
and then you're
telescopic.
subtracting it all the terms by themselves, and then all you're left with are the n terms.
The thing where you
Basically, you know how I like to do? You know how I like to do swoosh swoosh?
Yes.
Pretend like I did swoosh swoosh like a gazillion times
Yeah, that's
to
what I
arrive
You
at that
went
result.
swoosh swoosh, I think P minus 1 times.
P minus
P minus 2? It may be P minus 2, but I think it's P
Figure it out.
It
One more
doesn't
question.
matter, I'm not counting this.
So, point. All right. Let's. Oh, okay, we're gonna get x to the p plus, or no, just 1 x minus 1. So we're gonna get x plus x squared plus x to the p plus x to the p plus 1 by multiplying all of these terms by x.
Shouldn't you not get the next two plus one?
You should be getting.
Oh, sorry, x to the p is the last term.
Yeah.
You have two x, two p's.
Shut
I
up!
already wrote it.
Minus 1 minus x squared minus minus x to the p minus 1. Swoosh, 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 swoosh.
You cancel the
That, swoosh, swoosh something there. We're left with x to the p minus 1.
Okay. Thank you.
That's totally legible, Parker.
That's not, shut up.
No, I did.
We're moving on. So, we're not going to prove f of x is irreducible. We're going to prove f of x plus 1 is irreducible.
But then,
Dr. Ursel, why would you do such a thing to us?
because then you're gonna just get X in the denominator.
Because then
Swoosh, swoosh.
we just end up with 1 over x times x plus 1 to the p minus 1. Which in turn is just going to give us 1 over x times binomial theorem time. Sum from
Oh, God.
r equals 0 to p minus 1. P choose r, x to the p minus r. Minus 1.
Good luck.
Peace.
Here's minus 1, so.
Shouldn't that just be the P?
Will you make it more work to find it?
Let's see, if r equals 0, then we get x to the p, which is 5. If r is equal to p minus 1, we get
X, so
x
don't we want to go all the way to P?
to 2. But if we go all the way to p, then we
Or
just
do
get a
we
plus 1.
Do we just want to subtract
We don't-
that whole thing?
Well, I mean, if we go all the way to p, then we get the plus 1 at the end, which goes away because we also have a minus 1.
Yeah.
Yeah, I just realized in my notes I did not account for that at all.
Don't forget to add in the minus one.
I mean, it would
Yeah,
still
what
be the same
about
as
minus
three coefficients.
Yeah, I mean, that looks not wrong.
It has to
X
include
plus one, like, you
Yeah,
don't get
because
to
we're
just
gonna
do-
divide
Oh,
by
right.
x at the end anyway,
Drop
we
x
have
plus
multiply
one.
the whole thing by
Oh,
1 over
right,
x, so
but
it
yeah,
doesn't
but-
matter
so
which
it's
x
going
it
to
is.
get
You're good.
minus
That's
one.
what it is.
You're good.
Yeah.
We are going to
What?
get it.
Let's see if I can see.
The last term is going to have a power of x to the 1, which is fine, because then we're going to divide by x, which will get rid of it, and then we'll have a constant term at the end.
Yes, but does it not need to be negative 1?
No, because we have x plus 1 to the p, which is going to end in a 1, and then subtract 1, so that goes away.
Okay.
That's what we're doing.
Isn't that last minus one supposed to be
I mean, then you're gonna end up on
Not
the one when you
in
put
the
x.
power?
No?
What?
It'll be.
No!
You just distribute it.
I just distributed 1 over x up to all the terms.
Oh, I see. Never mind.
Yeah,
Okay.
1 over x is just getting distributed. Alright, so, what do we know about all these things?
They're all divisible by P,
Except
except the first one,
In the
the
last
first one.
and the last one by P squared.
Bingo.
Yay!
So, since
Congratulations.
p choose 0 is equal to 1, it's p factorial over p factorial times 0 factorial, so it applies down to 1. Which is the same as, which means that p does not divide p choose 0. And p divides p choose r for all 1 less than or equal to r less than or equal to p minus 1.
Which we painstakingly proved on that other theorem.
Which we painstakingly proved already from, forget what theorem it was.
Some theorem.
Oh, that was the freshman exponentiation theorem.
Yeah.
So I'm not going to prove it again. And p squared does not divide p choose p minus 1, which is just p factorial over p minus 1 factorial times 1 factorial. So you know, p. This is irreducible by Eisenstein. P equals P. There, I didn't do one where P explicitly equals 5.
So, does it matter that this is f of x plus 1 and not f of x?
Correct.
Huh?
It doesn't matter. Well, don't clap yet. We're not done because I have to
Oh.
explain. I have to explain that comment.
Oh, shoot. Why you gotta do this?
Oh, very, very deep. So let's look at why that is.
Open the question.
Well, let's say f of x was reducible, meaning f of x we could write as being equal to g of x times some h of x, where g of x and h of x are smaller in degree. What does that tell us about f of x plus 1? Andrew?
G of x plus 1 times h of x plus 1.
F of x plus 1 would also have to be reducible if f of x is. Just replacing all your x's with x plus 1s.
What, but x plus 1 is just a symbol. You actually have to do
X
work.
plus 1, what? X plus 1 is just a symbol?
If you just
Yeah, it's
rename x plus 1 as like y, f of y is irreducible.
These are just representations.
So what matters here?
That's
What matters here is that the degree of this equals the degree of that, and the degree of that equals the degree of that.
It's just
Yeah.
substitution.
If we couldn't do this with like f of like x squared, for instance, because f of x squared and f of x squared could potentially have like a different degree than f of x.
Yeah.
So that wouldn't necessarily work in that case, because you could have in that case, these are non-constant, but one of these would be forced to become constant if we did this with like x squared instead of x. But just swapping out x's with x plus 1s, the degrees are the same. So if these are both non-constant, these will be non-constant as well. Nice. Not clapping.
As the prophecy has foretold.
This gives us a whole class of irreducible polynomials, and the fact that these are irreducible is going to be very, very nice for us in a month's time. Ish. Galois extensions require simple-time polynomials to be irreducible, so.
We just name dropped the course. Oh my goodness, roll credits.
Yeah, believe it or not, we are actually going to talk about Galois things at some point in this Galois theory course.
Crazy.
Literally everything thus far has just been introduction, so that actually in Thursday's class we'll start doing Galois theory proper. But first, let's talk about our last trick. Because there's one other trick we haven't talked about for showing something's irreducible using Eisenstein. It's very devious. The trick is, instead of going from Q to Z, let's just check irreducibility over Z mod P instead. Take our polynomial, reduce it mod P. And in certain cases, if you reduce it mod P and you get something that's irreducible mod P, then the original has to be irreducible as well.
This sounds like it would be very useful for those cryptography things you were talking about with hundreds of digits.
Yeah, it sounds like it would be incredibly useful for doing that. So let's look at our next theorem.
They said you ever hear of the nifty helmet key exchange. Anyway.
Oh, yes.
I'm curious, but I'm not that curious. So let's let P be prime. And f of x an integer polynomial of degree non-constant.
Oh. Well, that makes sense.
And then we're gonna let
As if you want to.
f of x bar and, wait for it, Parker, polynomial ring over z mod p be obtained by reducing the coefficients of f of x mod p.
Parker, you look sad.
So you want 0.
And then it turns out that as long as the degree of f of x doesn't change by reducing its coefficients mod p, and f of x bar is irreducible, then f of x is reducible.
Because then P is not divisible by. Or AN is not divisible by.
Because it doesn't matter. It's perfectly fine to just disappear a large number of coefficients.
How do you worry about P squared?
How do you worry about p squared?
Yeah.
Oh, we're not using Eisenstein to prove this one.
Oh.
We're not?
Cool.
Turns out this one doesn't need Eisenstein.
I guess it wouldn't.
We'll
be
use
worth it, would
Eisenstein.
it? Because everything would disappear except for the first term if we were using Eisenstein.
Yeah.
Yeah, in that case, it wouldn't be super helpful. Eisenstein is not super helpful with these sorts of calculations, but this does give us another technique in our arsenal. So let's look at an example before we do our proof. Let's do, I don't know. Oh, I should have actually written down an example. Other than this one on the back that's more complicated. Let's do 7x cubed plus. Hold on. Hold on, I need to check something here really quick. What's he writing down, Parker?
X squared plus X plus 1.
Okay,
Yes.
7x.
Wow, that's so
It's
profound.
so cyclotron.
You don't know the half.
And now there's an X
Can I know
cubed
the
in
full
front.
answer?
Yeah,
Oh,
no, it's not.
crunchy.
No,
Yeah, it is.
no, it's
Let's just do 7x squared plus, I don't know. No, let's do this.
Oh,
7x cubed
oh,
plus
oh,
8x squared
oh.
plus 9x plus 1.
7, 8, 9.
It came full circle.
Holy moly.
Full cycle. Full cycle.
Alright, shut up. Shut up, I have an example to do. Alright, is this thing irreducible? I don't know. Can we Eisenstein this? Not really.
No.
Nothing divides 1, or no prime divides 1, so
Even
no.
if, what if we swap, reverse the order of them using the trick we did earlier?
Yeah,
Still
it
doesn't work.
still doesn't work.
Because only
it's
7 divides 7, then
And doesn't divide 8 or 9. So frontwards or backwards, I don't know, maybe Isaac's figured out another trick of changing the order of the coefficients, but
Not yet.
you can't really Eisenstein this. So here's what we're gonna do. We're gonna reduce mod, we're gonna look at this in Z mod 2.
Well, it's maybe not enough to conceive. The order doesn't actually matter.
Maybe the order is irrelevant.
it's
I don't know.
gonna seem right though.
So what do we get when we reduce all of our coefficients mod 2? Well, we're gonna get x cubed,
1,
0,
1.
plus x plus 1.
Whoa!
Now
Wait,
you're
that's
doing
that one of those.
Oh, look, it's cyclotonic.
No, it's not.
No, it's not, it's missing an x squared.
Oh, oh yeah.
Can we make
But-
it?
but-
That's also another reason you don't know about yet. But
Also,
Ah.
4 would be the prime, and 4 is not prime.
that's strongly related to the reason you don't know about yet. Yes.
That's true.
So, I claim this thing is irreducible in Z mod 2. So, how can you check to see if a cubic polynomial is irreducible?
The cubic form.
The cubic formula. Shut up.
We should.
No, you can just check to see. You can just check root. You can just check to see if it has any roots. Because if it doesn't have any roots, then it doesn't have any linear factors. And if a cubic polynomial has no linear factors, then the only way to factor it is into a degree 3 times a degree 0, which means it's irreducible. We don't normally do this with an arbitrary cubic polynomial over the integers because checking if it has any roots means checking infinitely many integers.
This one's just
How many
weird.
things do we need to check?
2.
2. F of 0 equals 0 plus 0 plus 1 is not equal to 0. F of 1 is equal to 1 plus 1 plus 1, which is 3, which is non-zero in Z mod 2. F of x is degree 3 with no roots.
You have to technically check -1 as well.
No, because we're in
Negative 1 equals 1.
mod 2.
1 equals negative 1.
Oh, yeah.
Because 0 equals 2.
Wait,
Subtract 1 from each side.
So how do we know that it's not the product of two things with no roots?
Because what would it be the product of? It'd have to be either product of degree 0 and degree 3, or degree 1 and degree 2.
This is degree 3. Okay.
Yeah, this is specific to degree 3. If I had given you something of degree 4 here, this would be a harder problem. Because then we'd also have to check, well, technically it would still be degree 2 times degree 2.
Right.
With no roots, so f of x bar is irreducible in Z mod 2, or I should say over Z mod 2, which implies from this theorem that f of x is irreducible over all integers, and hence q. And shut up. And
Once we set it into the Zmod 2 world, are we basically have to just go through and like it since it ended up equaling just f of 0 equals 1 and f of 1 equals 1. So if it had hit an even number, then there would be roots for this.
well, then we'd have roots, and then it would be reducible, and then we'd be in a pickle.
But when we're doing all, if that f of 1 is not 3, it's 1 in this case, right?
Well, 3. Well, it's both. 3 equals 1 in Z mod 2.
Okay.
But whatever you can call it 1, you can call it 3, you can call it any odd integer you want. What you can't call it is 0. You can call it f of 0 if you want. It's either 0 or non-zero, and these things are the non-zero term. So that's a sneaky way you could show something's irreducible. Just look at it mod p for some appropriate p.
So why do we check just the f of 0 and f of 1?
Because those are literally the only elements in the ring that we could
Oh.
possibly they could possibly be.
0 barring 1.
The only possible
Right.
roots are 0 and 1.
Right.
Either of those. Yeah. Thing is, you can't do this over the integers because you'd have to check infinitely many integers technically to see if they're roots. There's ways around this using rational roots test, etc., etc.
And you could probably narrow it down to if there is
Mhm.
an integer root, it's gotta be in this range, so it gotta just like these 10 integers, and if they don't, but
Yeah, just Zmod 2, only have to check 2. Zmod 3, you only have to check 3. Zmod p, you only have to check p of them.
Nice. Well, P is massive.
Say what?
It's not.
Well, I mean, if you have a very large p, then yes, this could still be quite tedious.
Like you.
Well,
Like the one in the homework that I gave you where you have to do where you have to do with mod 107. I'm kidding.
Thank you.
I was actually going with darn too if there was a quicker way to do this, but I'm not sure there is.
So let me ask you this. I don't want to print this. We can print this next time. But I'll ask you this. Is this an if and only? No, not that one. This one. What about if if f of x bar is reducible? Does that mean f of x has to be reducible?
No,
Can you give me a counterexample, Emily Rose?
no, not that quick.
The fact that I didn't state it as an if and only if makes you strongly suggest it's not, though?
you
Yeah.
asked about it for that matter.
The fact, oh, I mean, I could ask about it.
No.
I need to be less predictable. Turns out, no, the converse is not true. And here's a counterexample. Let's take x squared plus 1. Did everybody agree that that's irreducible over q?
You're gonna have to prove it for me.
Quadratic formula, I, a negative I, only complex roots, therefore no real root stuff. And quadratic, no real root
I
stuff.
feel like we proved it.
I don't believe in the quadratic formula.
I don't believe in you, yet you're still here.
Oh.
But let's check in Zmod 5.
I prefer the critique.
Let's use the quintic formula.
The whole thing is redundant.
General Quentin formula, yeah.
Alright, Eleanor, factor this for me.
Oh no.
In Zmod 5.
It's
Isn't that just x squared plus what?
I have one. What if x equals 2? Then x squared plus 1 is 0.
Oh, so this has a factor of x minus 2. Ooh. What else does this have a factor of?
X minus
3.
oh.
If you multiply this out, you get x squared minus 5x plus 6. And negative 5 is equal to 0 here, 6 is equal to 1, so you get x squared plus 1. So if it's irreducible over Q, or the integers, or whatever you want to call it, then it doesn't have to be irreducible mod P. But if it is irreducible mod P, and assuming this condition holds, then it will have to be irreducible in the larger ring.
Again, it's like find a prime that this works.
Yeah.
It's not necessarily just one prime.
Hence, if I give you homework problems, I would suggest trying small values of P to get the job done.
like 5.
That's
It's
actually my
just-
favorite.
How many?
5 is a large example. I mean, like, try 2 and 3.
What about 17?
For P.
If you want to try 17, Eleanor, go for
I
it.
still want to know why.
Probably if you can go through all the work, I'll probably just give it to you because I don't want to actually read the book. It'll probably be like 10 pages
Wait,
long.
does this apply to all problems?
Eleanor did
No.
excessive amounts of work.
In order to not do her
No,
work.
Alright, I'm going to tell you all this. You have everything you need now to do, we'll prove this theorem next time. It's not a very long proof. But you have everything you need to do the homework. So the homework has a couple questions about general irreducibility questions and like one thing where I make you factor something over several different rings. The bulk of the homework though, like number 3 on the homework is like, here's 5 polynomials. Prove to me that they're all irreducible over Q. And you might have to do some you might have to play around with several of the tricks we've looked at today in order to get there. Or maybe you can just get by with one trick over and over. Who knows? Have a good one, everybody. See you all on Thursday.
I know, I tried.
In the video.